Hey folks, welcome to the new episode on Clear My Paper. In today's episode, we are going to talk about area of a triangle using determinants. Another interesting concept. I don't know how much is the weightage in different exams, but usually a problem comes from this, and it requires an understanding of the previous concepts of what is a determinant and all those things. And that's the reason I've kept this topic towards the end of this whole syllabus on matrices and determinants. So let's talk about determinants and how to use determinants to find the area of a triangle. And as a quick reminder, all these videos are on YouTube, and in case you're interested in downloading the PDF version of all these notes without my doodles, a clean version which can be a reference for you, just email me to clearmypaper@gmail.com and you should get your notes free of cost. Okay. All right, let's jump into that. So area of a triangle, that's kind of the context of today's discussion. So for simplicity, what I've done is I've drawn an area of a triangle, and since we're going to use a lot of geometry, and in the backdrop I'm using the y and the x axis. So let's say we have a triangle with three vertices A, B, C, and we have the coordinates of each of the vertices in x and y format. And our objective is to find the area of this triangle using determinant. We know that there are a lot of ways to find the area of a triangle. The most famous is half into base into height for a right angle triangle. Otherwise, there are other areas, other methods also. But today we are going to focus on the determinant method, which is one of the applications of determinant, and how beautifully it kind of computes the area. And let's focus on that today. Okay, so if you go to any textbook definition, right, if you open up any textbook, more from an exam standpoint of view, there is no context, right? The first thing that they will let you know is formula for the area of a triangle using determinants is equal to plus or minus half multiplied by a 3 by 3 determinant, which is the first column is all of the x variables, the second column is all of the y variables, and the third column is 1. That's it. There is no intuition. And if that's what you want, and if you want to save time, and if you're okay with this, then you can skip the rest of this video. You don't have to watch this because I'm going to give you some intuition what's going behind the scenes. But if you are the person who wants to understand a little bit of intuition, have a mental map of how things are shaping up, then you can just follow along with me on this video. So and I'm going to skip the portions in the red because towards the end I'll be repeating this. For the timing, you skip the portion in the red. So if you see for the folks who are interested in getting some perspective behind the scenes, the above formula is very, very boring and dry. It's no fun. It's just like you have to mug it up, you have to by heart it. It's a rot way of learning, which is nothing bad, but if you're not from that camp, it's going to be difficult for you to do that. Now, instead of using this formula as is, as prescribed, let's do some circles, let's do some simple geometry and get a better intuition of where this is coming from and how do we think about that, and just get some sense of accomplishment in terms of, aha, okay, this is how I'm getting it, and which will in turn let you appreciate the beauty of matrices and determinants in general, like we have been doing in the past few videos. Okay, and as a full disclosure and disclaimer, this is one of the sites that I've referred here. I put the link. I think the name of the gentleman is James Lecture, and from Richland Education. I've just borrowed some of his concepts and the way he has put, and some of the images are coming from there. In case you want to refer to the source, that's the link I've put. So that's a full credit to the person who has put this, and thank you for that. Okay, let's take a simple example. Okay, let's say we want to find the area of a triangle whose vertices are given as this. There are 3 points and there are 3 vertices. And for simple purpose, I've drawn this triangle against the backdrop of x and y axis, and I've taken all these points. You can take these points in any order, but since we have the positive negative and we are drawing it against a backdrop of an x and y axis, I've just put it linearly. Wherever negative is there, I put negative, and wherever positive is there in the respective quadrants, I mean. And another thing is, if you see the backdrop of this page, you see all these blue squares, right? You can take this as your mark of units. Each block is 1 unit in length and 1 unit in height. Like this is the x, for each x value of each unit is 1, and similarly for y. You can take that so that we can count the blocks. For example, if you see here, the x-axis is 2 and the y-axis is 3, although this is not symmetrical, but if you can take this 1 unit of square as one distance of 1, then we see that we're roughly coming at 2 units, 1 here and 1, this 2. and that's what this unit is 2, and the y coordinate is 3 because we have 3 squares up, right? This like half a square, 1, 2, and half 3 kind of thing. In the bottom, I think I've adjusted the dimensions. It should be, I think, hopefully perfect. Okay, so let's understand that. And what I'm going to do is, now I want to compute this area of a triangle, and that's a problem. And before jumping into the formula that we have seen above, let's take a step back, let's take a small detour, and then come back to this. Let's assume for the time being that I'm going to box this whole triangle into a rectangle. That means there will be a rectangle outside, and I'm going to box this triangle inside. Okay, the way I put it here. Okay, and each of the coordinates I'm going to name x1, y1, x2, y2, and x3, y3 for sake of simplicity. And we need to generalize because we want to arrive at a formula because the given determinant is in terms of x and y. So we want to still generalize it. And we'll be kind of switching between the numerical calculation that we have in terms of the absolute values, and we'll also do the same thing using a generalized x and y formula. Okay, so now I've inscribed or I've embedded this whole triangle into this purple rectangle. Okay, and once I do that, what do I see? What do I get? The net effect of this embedding gives me a picture of the one that is in between is the area that I need to find. But surrounding that, because I put it inside the rectangle, I have a rectangular box outside. That's one. And then within the box, apart from the triangle for which we need to find the area, I have got 3 right angle triangles, which I have named as A, B, C, and I've color coded the yellow, the green, and the blue. And what we can think in a simple elementary way is the area of the triangle in question, that is given in the problem, is nothing but the area of the outer rectangle over here and minus the sum of these 3 triangles. So if I remove the sum of these 3 triangles and I also remove the area of the bigger rectangle, whatever I get remaining will be the area of this particular triangle that's in question, right? That's pretty straightforward. Okay, so let's follow that method and see where we land in terms of the formula. Okay, and as a quick disclaimer, which I'll be re-emphasizing 2 or 3 times all along this episode, is since we are going to talk about area, which is nothing but length into breadth or base into height, it's a measurement, right? So the area cannot be negative, right? Although there are some negative values here in this question, and there'll be some indifferences which you will see that it might throw up a negative value occasionally. We will just ignore that because we know that the area of a triangle or any length in general from a geometric standpoint cannot be negative because the length is a real thing, right? When we say it's 1 feet, it's 1 feet. When I say it's 1 square meter, it's 1 square meter, however it is. So we will just ignore the notion of numbers being negative. We are not dealing with numbers per se. We are dealing with numbers that represent length, breadth, and area, which cannot be negative. So keep that in mind. So the first mission that we are going to do is we are going to compute the area of this outer rectangle. That's the first thing we are going to do as per this formula. And we know that the area of a rectangle is nothing but length into breadth or multiplying both the sides. We know that. Okay. Now let's understand how are the sides computed. So let's take any of this side. Let's take this side over here. What are we seeing, right? The topmost end. So what is the length of that? There are 2 or 3 ways to think about that. The easiest way is, since you know that each square is 1, you can count the number of squares that will give us the length. For example, if I start from here, forget the slight misalignment, assume that it's all aligned. So if I start from here, this is 1, this is 2, this is 3, and this is 4, and this is 5. So roughly it's 5 squares, which is what I've got here. The length is 5, or I put 5. That's one way of doing that. The other way of doing that is, since this particular line or the topmost bottom is kind of parallel to the x-axis, so I can take the x coordinates of the 2 points of this point and this point, which is here, and the difference of the x coordinates between these 2 points will also give me the answer. For example, if I take x2, which is the point of here, which is 2, minus, if you take this point, this point is nothing but the x coordinate over here, although the point is here, but still the x coordinate is going to be the same because we're just considering something parallel to the x-axis. It's going to be minus 3. So if I just say 2 minus 3, 2 minus 3, the coordinate, I'm going to get the answer as 5 because it's going to be 2 plus 3. And like I said, whether you take x2 minus x1 or you take x1 minus x2, it does not really matter because we are always going to force the answer to be a positive because we are talking about a length. So that's 2 different ways of measuring it. One is you just count the squares because you can do it in the easy way here. Or you take, if the line is parallel to the x-axis, then you take the 2 points in question and just subtract the difference, and then you get the value. And similarly for y, you can again count the blocks, each square, and compute it. Like in this case, if I start from here, assume that this aligned to this line here, this square is 1, 2, 3, 4, 5, and 6. So I've got the answer as 6. That's the height. Okay. Alternatively, I know that if I take this line is parallel to the y-axis, and if I take this 2 point, this point over here, and this point which is slightly tucked in, but doesn't matter. If I draw a straight line, it is going, the y value does not change. So if I just take the difference of either y2 and y3 or y3 and y2, does not matter, because we're always going to take the answer as positive. Then the answer is both the y coordinates, 3 minus 3 is equal to 6. That's how I'm getting it, right? And that's what I've written here. One is I'm taking the absolute values and computing it, and this will be using in the down when we finally do the addition and subtraction. So we have the area of the rectangle as 30 square units. Let's always write that because that's more important, because we need to write the unit. It's area, so it's in square units. And in terms of x and y, since we're going to take the difference of x coordinates of the 2 points in question and y coordinates, the difference of these 2 points is x2 here and x1, and over here it's y2 minus y3. And the order does not change, but we are going to keep it positive. So let's assume that we're going to stick to this order. So it's x2 minus x1 multiplied by y2 minus y3. And when I open up the brackets and I multiply it, I get this expansion, which is x2 y2 minus y2 y3 minus x1 y1 plus x1 y3. There's a long formula, but I've written at the bottom again. So there are 4 terms that is going to come, and when I open up the brackets. Okay, so far so good. Similarly, what I'm going to do is I'm going to apply the same logic to find the areas of these 3 triangles, and I'm going to subtract by the number by this 30 and also by this equation which is in x1 and x2. So let's continue. Let's take one thing at a time. All right. Okay, so what do we have here? So let's focus on the triangle A. If you can consider this triangle A, all the 3 triangles are anyway right angle, but if you consider this triangle A, you can consider that this is like the base is upwards. If you can consider this as the base and this as the height. And the area of a right angle triangle is going to be half into base into height, which is going to be true for all the triangles. And how do I compute the base and height? If you take this whole height, which is same as the length of the rectangle that we saw here, nothing changes, x2 minus x1. So that's an easy concept. So I get x2 minus x1 here, and the answer is 5. I'm taking as the 5 unit here. And if you take this kind of base here, over here, right? So what is this? There are 2 or 3 ways. A, you can count the number of squares, in which case it's just 2 square, you'll get 2. Or what you can do is you can take this point. This is the point in question here, right? And this is the point in question. So this particular line is parallel to the y-axis. So I'm going to take both the y coordinates, and whatever is the difference of the y coordinate, that's going to be the base or the height of that. Or I can take the full length and subtract this. However you want to do it, you can do it. But assume that I'm taking both the points and a line parallel to y-axis. I'm going to take the difference of the y coordinates, which is given by y2 minus y1, which is going to be y2 is 3 and y1 is 1. So 3 minus 1 is 2, and this is what I'm going to get here. So when I do this, the answer is going to be 5 units because the 2 and 2 gets cancelled. And if I'm going to generalize this, I'm going to use the base and height in terms of x and y variables. I'm going to take this x2 minus x1 over here and y2 minus y1 over here, and again I'm going to expand it to get the 4 terms, and I get this, which we'll be using further down. So like that, we have got the area of the triangle A, and we're going to find the same way B and C. So I'm going to just speed up a bit here because now you're getting the drift of where I'm going. Similarly for B, what I'm going to do is, if you take the height over here, I can count the squares. It's 1, 2, 3, 4, 5, and 6, which is what I've taken 6. Alternatively, since this is like parallel to the y-axis, the whole length is going to be difference of the y coordinates of the 2 points. So which is y2 minus y3. I'm going to take the difference. Again, it's going to be 6. I've taken that. And the base, it's not the whole base here, right? We know the whole base is the base of the rectangle. We don't want the whole base. We just want the base or the difference between the 2 points in question, which is this point over here cross and this point over here, and that's nothing but it's parallel to x-axis. So I'm going to take the difference of the x coordinates of both the points. However I take it, the difference is going to be positive, or I'm going to make it positive. In this case, I'm going to keep it x2 minus x3, which is 1, which is what one I've written here. And I applied the same formula in terms of base and height in terms of x and y over here. Okay, and I get this expansion. Similarly for C, the triangle C, I'm going to calculate. Okay, C is going to be interesting because you already done half the measures. You know this measure here. You know the whole measure. You can take the difference, or you can count the squares, or you can take the points of this and this over here, and you can take the difference of x coordinates to give you the base, which is going to be over here. See, that's a demonstration. So if I do x3 minus x1, x3 is 1 and x1 is minus 3, and what's going to happen is it's going to give me a negative value of minus 4, and I'm going to take it as a positive value because I don't want to keep it negative. I'm going to take it as a positive value. That's what I'm doing here. Okay, over here I think it's a negative 1, I think, not 1. Let me check here. My handwriting is okay. Where is my value here? Okay, it's 1. Okay, let me see what's going on here. Okay, so if I take the value, so if I say x3 minus x1, if I take x3 minus x1, it will be technically 1 minus 3 over here. It should be 4. But I've taken x3 minus x1 to prove a point that it does not really matter. Basically, I've not taken x3 minus x1, sorry, and this is x1 minus x3, sorry about that. I'll just change it. This is x1 minus x3. Okay, I'm going to rub this. Okay, this is x1 minus x3, where I've taken minus 3 over here, and then minus the positive value of 1, which gives me minus 4. But like I said, we are talking about the length, so I'm just going to disregard the negative sign, and I'm going to take 4. If I'd switch the points, taking 1 first, it would have automatically given me the answer 4, right? But I've taken this one and I have just computed this value like this. Okay, so it does not really matter. And same thing I'm going to plug in here to calculate the area. The area is 8 square units, and I've taken y1 minus y3, and I'm still taking x3 minus x1 because it does not really matter. I'm just taking I'm showing here x1 minus x3, but I'm going to take here x3 minus x1 for calculation purpose. Okay, it does not really matter. So I have all the 3 formulas. I have all the 3 areas in absolute numbers, and I also have the formula in the generalized way. Okay, now let's see where we are going with that. So what I'm going to do is I'm going to add up the areas for all these 3 triangles and then subtract it from the rectangle. Okay, so what I'm going to do is all these things that I've copy pasted from the reference side, I've told you area A, area C, area B, and area A over here. I'm going to take all of them and add, and if you see, the half is common, so the half comes outside. So this is the area of triangle A, this is the area of triangle B, and this is area of triangle C over here. I've just copied it and pasted it, and I'm going to cancel out the common terms. And the way I've done is, if you see, wherever I underlined with the common lines, number of lines, it's the same term. So we have x1 y1 here, we have x1 y1, I'm cancelling it. Then we have x3 y3 here, plus x3 y3 minus x3 y3, I'm cancelling it. And x2 y2 is also common, x2 y2 and x2 y2, but it's not a negative, so it's x2 y2 and there's a plus sign here, so it becomes 2x2 y2 over here, 2x2 y2. And then the half is still common, so I'm separating out that term, so which is half from coming from here, and 2x2 y2, and plus half of the remainder of the terms which is pending, which is this, and this, sorry, not this over here. Okay, and again this 2 and this 2 gets cancelled, we don't need that, so all we end up is with x2 y2, and plus we are going to have this kind of clean term over here. So now what we have done in essence is we have computed the area of all the 3 right angle triangles over here. Okay, and we are going to take this whole thing, this is A plus B plus C triangle, right? I'm going to take this whole thing and subtract it from the area of the rectangle that we kind of got above. I've copied the formula as it is here. This is the area of rectangle, and this is the area of A plus B plus C triangles. Okay, so I'm going to subtract it so that I get the area of the triangle in question, the center part of that. Okay, that's what we're going to get. And if I expand it, if you see right at the outset, x2, y2 and x2, y2 gets cancelled. I've crossed in red, and that's the beauty of the symmetry, how it kind of collapses. And for the remaining things, we just get this variable over here, right? All these things. And if you see, there are a few variables that are repeated here. So on this side of the equation, we have the whole number, and at the other side of the terms, it's half. And if you see the way I underlined it, if you say this one single underline and this single underline over here, this x2, y2, x2, y3 is coming from here, and this half x2, y3 is coming once I open up the brackets and get the half inside. If you take this, and if I take this minus into minus becomes plus, then becomes plus x2, y3. And so if I have to add this minus 1 x2, y3 plus half x2, y3, that gives me negative half. So a lot of terms will be lost because we are going to, each of this term has a representation over here, and we are going to remove half of that, and we are going to do the positive negative signs accordingly. So if you do this, we get this equation, which is a cleaner version of this, where you see everything has again that half, and then if I take the half common out, this is what I get, a simplified version of that, right? This simplified version of the area of the required triangle in question. And I'm going to simply rearrange these things in this format, which I can do. There is nothing wrong about it, right? For example, x3, y2, this term over here is over here. I'm going to bring it first, and I'm going to subtract x2, y3, which is the first term. So the number of terms still remain the same. I have 1, 2, 3, 4, 5, 6. I've got 1, 2, 3, 4, 5, and 6. I'm just rearranging it. And you'll notice the way I've rearranged it, there are few terms here, and there's a negative sign. There are again few terms, again there's a positive sign. It kind of gives you a flavor of finding a determinant of a 3 by 3 matrix, right? Determinant of 3 by 3 matrix, which is what it gives, which is where each of these terms is like a 2 by 2 submatrix, which we'll come to, and then all the coefficients are 1 over here, right? So it makes a 3 by 3 matrix, and that's how we're going to connect the dots, why this ties back to the formula that the textbook normally gives and where that's coming from, okay? But we are not there yet. So hold on to this thought where kind of we have arrived at this, and we're going to call this as equation 1 in green color, which is nothing but the area of the triangle in question, okay? Now, let's take the textbook definition, or even if you assume that you're going to just get a matrix or a 3 by 3 matrix out of thin air, and this is how you're going to construct it. It's half, and I've got the first column as x variables, the second as y, and the third column I'm going to keep the coefficient of 1. That's it, okay? Let's say I'm going to do this way, and I'm going to find the determinant of this 3 by 3, okay, across the third column. This is what I'm going to use. Third column is this is the third column. I'm going to use this, and I'm going to find the determinant of this matrix, okay? It doesn't matter how you find, I'm just going to use the third column. And this half, for the time being, you ignore it. We're going to carry it everywhere for the time being. So this half comes here. Now if I have to apply the determinant, okay, so what I've done is, this is the actual formula that we will get, and how are we going to get it is kind of a simplification, where I have highlighted in yellow each of the element that needs to be excluded while we calculate the determinant. In this case, it's 1 and 1 and 1. So I'm taking the third column. So each element will go off, and whichever row and column they are presented, which is in yellow color, we need to exclude that, and whatever is the remaining, that will be the 2 by 2 determinant, like which I mentioned. And this half I'm just carrying forward as it is for now, and the coefficients are going to be 1. And since we're going to have the cofactor effect, it's going to alternate between positive and negative signs, and we're going to find a determinant or a submatrix of each one of them. And when you multiply this, like if you say diagonally x2 minus y3, you get this minus x3 minus y2. So this exactly will roll into this formula. So I've written the formula first, or the final determinant of this left hand side matrix, and this is how we compute. This is like a recap of what we have done, so no big change. So now we have got another equation. So now we have got two equations, one which is coming out as a part of this kind of a 3 by 3 determinant or matrix, or determinant of a matrix, and the other one, which is equation number 1, which kind of we got it geometrically, where we moved things in x and y and generalize, and we are getting this. And let's try to find out what is the similarity between these two formulas and what is not the similarity. So I'm going to copy equation 1 and equation 2 in green here, Okay, and this is what we have. This is the geometric version which we calculated, and this is using the determinant formula which we just expanded. So if you see, it's almost similar, and let's make some quick observations. Okay, it's almost similar in nature. We have the half year, we have the half year, and we have got 6 terms, we have got 6 terms, we have got alternating minus and plus, we have got alternating minus and plus. So those are the similarities, so they match in those respect. And let's figure out where are the differences. So the differences are in the algebraic sign of each of the term. For example, if you see x3 y2 is positive here, and over here it's negative, and x2 y3 is negative here, over here it's positive. Those are the differences across each of these terms for the most of it that we find in this equation. And the reason for that is because how you choose the variables. The question had 3 vertices, and we randomly assigned them x1, y1 and y2, correct? The question did not tell which one is this. These are the 3 vertices, and we randomly assigned. So I could have picked up anyone as x1 and y1, or anyone as x2 or x3, or vice versa, and that would have changed the whole equation of what is the computation. But we picked a particular order, and that's the reason there is a notable difference in the algebraic sign. That's number 1. Okay, the order of the selection matters. Okay, and the other thing is, if you remember, since we are going to compute the area or the length or the base or the height, and all of these are like difference elements, right? It does not really matter, because we saw from a geometric standpoint, doesn't matter how you compute the difference, the absolute value still remains the same. So in that aspect, we can assume that although these 2 formulas are exactly the same, except for some of the terms which have a plus or minus or vice versa, it should not matter, because we are still going to take the absolute value, because lengths and areas cannot be negative. The determinant of a matrix can be negative, yes, because of the orientation and all those things. But since the context is computing the area and the length, we are just going to ignore the negative part, and we are going to force ourselves to see that length or area as a positive item. And that's the reason these terms which have positive or negative or the opposite effect does not really matter, because we are not interested in the algebraic sign as a prefix. We are only interested in the absolute value. So that part of the puzzle is also solved over here, which I mentioned here. Absolute value matters, so ignore the negative value. And for that effect is why the textbook definition, if you see over here, till now I have not brought the plus or minus sign here, but if you see the textbook definition that was given in the beginning, they had put positive, negative here, and that's the reason I told I'll come back to that in the end of this video. I did not talk about that in specific over here, the positive or negative, because it is just telling you that after you compute the determinant, don't worry about the positive negative sign for now, don't worry about the half also, we can compute it later. After you compute the determinant of this particular matrix or 3 by 3 matrix, if the determinant of this 3 by 3 matrix is negative, then you apply the negative sign here, and negative minus negative becomes positive, and so the final answer becomes positive. And if the answer over here, determinant, is positive, then you don't have to do anything, because we want the positive answer. So the plus or minus sign just indicates that this is like a joker in the deck or a wild card, which you can use at your will and discretion, however it works, to make sure that absolute value of this determinant always stays positive in the context of computing the area. So it's just one answer. It doesn't mean that you have a positive determinant and you have a negative determinant. Don't get confused. It's just telling you that use your discretion to choose any value you want, as long as you make this value positive. That's all it means. And that's as I said, I'll come back to that later. Okay, that's all I wanted to sum up on this kind of video. I'm going to put a part 2 of this because I have some more things to cover, but let me go back to where I stopped. So this is where we left over, and that's what the definition of area of a triangle using determinant means, which is plus or minus half, which you'll use at your discretion. The first column is x variables, the second column is y variables, and the third column is just unit or 1. Okay, that's how it is going to come, and there's going to be square units as a measurement. In the next part, what we'll do is we'll take all these methods that we applied, and we'll just put back the values to make sure that whatever we are talking, that makes sense and the answers are tying out, and that's what we will do. So we'll continue this in the part 2 of the video. Thank you guys. I'll see you on the other side.